Okay, so welcome everybody and Happy New Year. So I will just take a few minutes to talk to you about the new initiative that was launched actually just a couple of days ago. And this is a mentoring initiative. It is endorsed and supported by the SIAM Activity Group in our field, and also by the Bachelet Finance Society. And what we would like to do through this initiative is provide a platform for the young people, young researchers who are at the early stage of their career. And we would like this platform to be a platform for support, for guidance, for mentoring. So we are looking for pairing mentors and mentees. And mentors will be senior people from our field, and the mentors will provide advice to their mentees on a variety of professional matters that are related to career development, grant funding, promotions, tenure requirements. We felt that there is a big array of issues that many times the young people are not familiar with, and to have an organized place where this matching can happen and the advice can be given from the mentors to the mentees will enrich a lot our community. And how did this start? How did this start? Actually, it started as a pilot mentoring program at the SIAM FM21 conference. And a number of early career scientists were paired with senior scientists in our field. And this was extremely well received by both the junior and the senior groups. And we got very motivated by the success of this pilot program. And with the steering committee members, who is Beatrice, Francesca, Igor, Uimeng, Birgit, Stefan, and Ludovic, we spent some time organizing the mentoring initiative. And you can find information about this. I will give you the links in a minute. So for now, this mentoring initiative is open to young researchers who come from underrepresented groups. On the other hand, depending on our mentoring resources, our mentoring capacity, we expect to open the program to all the young researchers. And when we talk about underrepresented groups, as it is usually the case, we think about several groups, but these are not limited to. And we would very much like to invite young researchers from this group to join the program. How to participate? You can go to the website. I don't know if you can copy it now, it doesn't matter. You can go to the SIAM Activity Group website where we have posted the announcement. You can go to the Bachelet Finance Society site where the announcement is also there. And you can go to my website, or you can also go to the website of the members of the other members of the committee. And what you're going to find there, we will have the forms for the mentors, and I cannot stress enough how much we count on senior members of the committee to become mentors. And also, if you are interested in becoming a mentee, then we have the mentee form there, and we are very much looking forward to having you. Now, the program will be operating in a rolling horizon format, but if you want to be involved, included in the first round of matching, let's say, then I think then the deadline is more or less a month from now. So we are very much looking forward to having you, both the mentors and the mentees, this is a program that speaks very strongly to our hearts. So I sincerely hope that it will be a very successful program. We will put a lot of work and a lot of care in it. All right, so having said that, I think we can move ahead with that.
Can I ask a couple questions about the program?
Maybe not now. Igor, what do you think? Because I really don't want to take time from.
Probably just I think,
Like an email, sure.
Yeah,
an email, but if it's very short, Harvey, sure, why don't you? But it's short question, short answer, then that's fine, maybe.
Yeah, we have
Well,
posted a very detailed information.
I went through that information, already, so I still have questions, though.
Okay.
I guess this is for, doctoral students and past that stage, right? So, what is this providing that wouldn't ordinarily be provided by their advisor?
All right, so this is a long question, so I can.
Okay.
I will.
So maybe we can follow up another time.
Of course, and
the other question was, is this geared, you say, for supporting their career? Are you talking about an academic career, or are you talking about an industrial career?
It can be both.
Okay.
All right.
So I think as Harvey, to clarify, as we emphasize, it's researchers. So deliberately we named researchers, not to say academics or something. Yeah. So it's geared to both. So.
Okay, thanks.
Sure.
Thank you. So Thalia, thank you very much for introducing this. And as we all know, we are really kind of hope is that we'll have a great success with this. And I already posted the link. I think I posted to everyone. Somebody is asking, I can post it one more time, just to everyone. And we move to the topic. Yes. So you should have now the link to the website where you will be able to find the forms and the detailed information. So thank you very much. Now we can move to the next part of the seminar, the talk, today's talk by Daniel. And it is my great pleasure to start this seminar with speaker Daniel Lacker, who is at Columbia University. We've been knowing for some time each other, and it's always very interesting to listen to his talk. His research, of course, is well recognized. I want to mention that he is sort of a disciple of the SIAM Activity Group. He received our prestigious prize several years ago, which is the SIAM Conference Paper Prize. And it's very nice to see that has a flourishing trajectory. Now he also has the Career Award, the NSF Career Award, which is saying something big. And today, Daniel will talk about his main topics of research, which is mean field games. And Daniel, would you like to share the screen, perhaps?
Yes, sure. So you can see it?
Yes, and as always, the rules are the same. The talk will last approximately 50 minutes, 45 minutes. You can ask questions in the chat. Preferably, you should be able to type them, and I will either ask you to ask them live, or I can read on your behalf if you don't want to speak up. And with that said, Daniel, the floor is yours. Thank you.
Okay, thank you very much, Igor, for the generous introduction and for the invitation. It's really a pleasure to kick off this excellent seminar series for the year, which I've enjoyed following. And let me thank the SIAM Activity Group leaders, past, present, and future, for carrying us bravely through these challenging past couple of years. So I'm going to talk about exactly this topic that I got this recent grant for that Igor mentioned, which I think is a very exciting new direction for mean field game theory, which is to incorporate graph structures and more general heterogeneity into the interaction. So I'm going to start with maybe 10 or 15 minutes of a more high-level discussion of this new direction that myself and a few other groups have started to push toward. And then I'll turn into a more specific case study that there is a paper about and some, concrete mathematical results that will illuminate some of the, the first sense of, what kind of phenomena we can expect, what kind of issues, challenges, results will we run into with this kind of new direction of mean field game theory. So to start, let me mention that this work that I'll be discussing is joint with my talented PhD student, Agathe Soret, who's graduating this year. And okay, so at a high level here, I'm not really going to assume you're a mean field game expert for this talk, but this is definitely the jumping off point, the motivation or inspiration for the work here. And I think by now the theory of mean field games has become quite well known in this community. It's really by now a very widely used framework for modeling and analyzing large scale stochastic games. Now, economists for decades before had been working on models with games with a continuum of agents as a kind of convenient, more tractable idealization of a large population model. And really these contributions from Lasry-Lyons and Keynes, Swang, and Malhamé kind of, well, one brought this into continuous time, but more importantly, really gave this a systematic mathematical framework that's easy to adapt and apply in different contexts. Okay, so this mean field game framework is really a great tool set to be familiar with if you want to model a large scale competitive system. But there's one key structural aspect, a kind of necessary feature or ingredient you need in order to carry out a mean field analysis, which is some kind of symmetry or exchangeability. And it's precisely this key point that I want to poke at in this talk and this new research direction. So essentially, mean field game paradigm is limited to models with homogeneous or symmetric interactions. And I want to stress also the word interactions here, because you can incorporate plenty of heterogeneity into the individual characteristics in mean field game models, right? Players typically have their own IID sources of noise or randomness, and you can assign different types to different players to give different players different characteristics, but the nature of the interaction still needs to be symmetric. We all interact equally with everybody else in a traditional mean field model. Okay, and economists sometimes use the term anonymous games to refer to this, the idea being that somehow the names are irrelevant. Okay, so I don't care what strategy Igor is doing versus what Thalia is doing. What I care is what the group of people, in a distributional sense is doing. I don't care who is doing what exactly. Okay, so this is the limitation that we want to push past with this new direction of work. And the easiest way to think about, how would we understand or model heterogeneous interactions is really through graphs. And this is the framework I'll focus on, but you can, generalize beyond that in various ways. But so let's imagine now that, different players give priority to each other in certain ways. So the players will now be identified with the vertices in a graph or a network, and the edges or connections in the graph represent the direct lines of communication. So I'm only going to, let's say, share news stories with my friends on Facebook, and maybe they'll share them with their friends, but my only direct contact will be with my Facebook friends. So it's this network of this Facebook network that governs the interactions in whatever we're modeling here. Okay, so I should stress the graph for me will not be anything with a spatial meaning here. We're not moving around on the graph. The graph just governs, who's connected to whom. Okay, now there are plenty of applications you can think of. I'm not going to really talk or focus on any specific one. There are, of course, a wide variety of network-based models out there that I'll touch on in a moment on a literature slide here. But you can imagine the spread of opinions or information through a social network. This is a sort of common topic studied in network models. I think in this community, a very natural application for a new framework like the one we're pushing toward here is in the modeling of systemic risk, where the players or vertices here will represent some kind of financial agents, and the edges maybe should carry weights and directions in this context. These would represent some kind of obligations debts between these agents. And there's a rich literature on systemic risk, that incorporates, realistic network structures, although a lot of the kind of mean field modeling, the large scale modeling systemic risk kind of has to ignore this network structure in order to get, to a tractable mean field analysis. So this hopefully might help to give a framework to sort of bridge the gap between the mean field and network perspectives on systemic risk. But this is a bit too vague that I shouldn't go into any more detail here. Many of you probably know more about this literature than I do. But consider this a kind of natural application for what I'm going to discuss here, which will be more focused on the game theoretic modeling. Oh, and let me just say, I know this is sometimes dangerous, but I encourage you to interrupt me if you have questions along the way. I find it helps break up the isolation of these Zoom meetings a little bit. So don't be shy if you have questions along the way. Okay, so this is sort of the high level context here. Again, I want to get past this homogeneity assumption in mean field game theory. And basically the guiding questions here will be, first of all, when can we just pretend there is no graph and get away with the usual mean field game approximation? What do I mean by that? Well, imagine, instead of having a model where everybody interacts equally with everybody, maybe Igor and Sebastian are not getting along, so the two of them will not interact directly, but everybody else will still interact with everybody else. And in a large enough population, this should not make much of a difference, and you could still approximate things with the usual sort of mean field story. And carrying this logic a bit further, the basic message here will be that in sufficiently dense networks, you can get away with a traditional mean field approximation. And I'll show you how to quantify this in some sense based on how dense the network is. Okay, so I see a hand raised from Sam. If you want to jump in, go ahead.
Hi, Dan. Just to clarify, so we're thinking here about fixed networks or random graphs, or just where's this going?
Good question. So I'll show you some math in another slide or two, but the network will be something static to me. So this will not evolve over time, which would definitely be useful in many applications, but would be a huge additional layer of complexity. The network will be static, but it can be random, but it will be, let's say, quenched. I'll talk about Erdos-Renyi graphs as an example a bit later. But we think of the realization of the graph as something fixed, and then we will play our game on top of that, basically.
All right, thanks.
Mm-hmm. Right, so key question number one will be, when can we get away with the usual mean field approximation? And the natural follow-up question will be, if we can't, if we're not on a dense enough network to do this, what can we do instead? Is there some kind of alternative limiting regime or some sort of tractable thing we can do in a large scale system of a different sort? And the graph structure will play a role here in figuring out how to encode some notion of large scale graph structure will be a key part of the modeling here. Okay, so the rest of this talk will zoom into a specific linear quadratic model. And this will be kind of simple enough that we can do things semi-explicitly and yet rich enough that it will give us some sense of how the network is coming through in an interesting way. Okay, so it took me many years in my career, but I finally come around to the wisdom that it's very useful to start with a worked out example before trying to prove super general theorems. So this is the spirit of the rest of the talk then, but I think the example contains a lot of the interesting phenomena already. Okay, so before I jump into that, let me mention some related literature to give credit where due, but I'll try not to be too verbose here. So in the past, I'd say the closest literature are these first two broader bullet points here. In the past few years, several people from the mean field game and related communities have been thinking in a similar direction. And when you're thinking of large scale graph-based models, it's natural to think in terms of various notions of graph limit theories that have been developed in the past few decades, or originating from combinatorics. But the most popular of these graph limit theories is this notion of a graphon, which gives you a convenient way to model sort of a dense graph with a continuum of agents. So these sort of models have been started to be studied in the past few years here. And I'll briefly comment on the difference with what I'm doing in another slide or two. There were also some case studies. So Francois Delarue studied this case of a dense Erdos-Renyi graph where basically the same mean field approximation works in this particular dense graph regime. And on the opposite extreme, this recent work of Feng, Fuke, and Ichiba looks at these models on directed cycle graphs. So where we're all, sitting around a circular table and whispering to the person to our right, let's say. And this is a very sparse graph, so on the opposite extreme. But this one direction of propagation makes some nice kind of tractable analysis possible. The work I'll talk about, we're able to cover a kind of broad class of different graphs to see how the structure plays a role. Some broader literature, but still relevant. In around the same time, going back to 2015 or so, some similar work has started in the context of basically the same kind of models, but without the control or game theoretic aspect. So if you take these interacting particle systems that are somehow the foundation of mean field games, but now you want those particle systems to interact in some sort of heterogeneous way, say as governed by a graph. These kinds of models have started to see some analysis in the past 5 or 6 years, in part by myself in the sparse regime here. And there's some interesting things to learn there. And reaching a little further afield in the probability and statistical mechanics literature, there's been a decent amount of study of more traditional spin systems, so static models on large complex graphs of various types. In some sense, it started because the integer lattice, let's say the true lattice models can be too difficult, but if you move to trees, things become more tractable in some ways. And then, social networks and other things made those kinds of models actually useful in their own right. So this has a whole life of its own, and there's a lot of inspiration to be borrowed from this literature as well. Okay, so without further ado, let me make this a bit more concrete and introduce the basic model setup. And the idea here is I'm going to write down a very simple stochastic differential game, which you can study on any graph. So if you give me a finite graph, I can run this game on that graph. Okay, and for me, for the rest of this talk, graphs will be undirected with no weights. So graphs are just a set of vertices and a set of edges between the vertices. And if, Igor and I are, if I'm friends with Igor, then Igor is friends with me as well. So this is a simple, undirected, unweighted graph. And if you give, a couple notations I should mention, DEG will mean the degree. This is the number of neighbors of this vertex V, the number of other vertices they're connected to. And this tilde symbol will mean, that this is an edge, this is a connection. Okay, now each player is named by a vertex in the graph. So player V has some state process in this model, which will solve this very simple, Ito dynamics here, where player V faces their own independent additive Brownian motion. You start from 0 to keep things simple, and they just control their drift directly. And to be concrete here, I'm going to work with Markovian controls, which can take the full information into account. I'm going to work with HJB equations to solve things. So this Markovian is a convenient choice for me more than any philosophical choice. This is a convenient choice. Okay, so the state process is extremely simple. We're all controlling our drift. And now all of the action takes place in this cost function. And this is where the graph really comes into the picture. The objective of each player will be to minimize this usual quadratic running cost, this energy term. So they don't want to exert too much effort in their control. But at the same time, everybody would like to be close to the average position of their neighbors at the final time T. And this constant C will control the trade-off between these two effects, minimizing effort versus being close to the average of your neighbors at the end of the time period. Okay, so in case the degree is 0, let's just set this equal to 0. We don't need to dwell on this, but this will be convenient later on when we want to include Erdos-Renyi graphs, for instance, which may have isolated vertices. You know, if you're not connected to anyone, then you just sort of do your own thing independently, and this doesn't make a huge difference, but let's just fix the notation here. Okay, so this is where all the action lies, is in this terminal cost function. And again, if you give me any finite graph, I can pose this stochastic game on this graph. The goal will be to understand what the Nash equilibria look like, particularly when this graph is very large. Okay, and to figure out what sort of more concrete mathematical questions we might ask here, the mean field game setting is again the natural starting point. So the mean field game case is when the graph G is the complete graph, meaning every vertex has an edge to every other vertex. So in this graph setting, the mean field case is the complete graph case. And by now, I'm going to review this briefly, but by now we understand pretty well how to do a mean field approximation here. This is a simplified version of this Carmona-Fuchs-Sun model. And this is a good example that I've taught in a class before. This is a good intro example for mean field games because you can compute the n-player equilibrium explicitly. You can take limits. You can see that it really gives you what you should get from the mean field model. So if you do all this, if you work all this out, you find exactly the Markovian equilibrium for the n-player game, which just takes the form of some time and n-dependent constant times the average minus your current position here. Okay, so each player just kind of pushes towards the average of all of the other players with some time-dependent rate, which increases the closer you get to the final time horizon. So the intuition, the structure of this is intuitively clear. The precise form of the constant is not very important for our purposes. You can send n to infinity here, and you'll find that basically the mean should go to 0 because everyone else started at 0. And at the end of the day, the mean field control policy, you just push toward the origin with some, again, time-dependent rate, as you can see here. So the precise form is not super important. There's this mean field control we can identify, and all kinds of forms of convergence happen here in the sense that, for instance, we can identify the distribution of the single typical player in the large N limit. This is, the control is linear, so this is an Ornstein-Uhlenbeck process. The marginal laws are Gaussian. We can compute everything here. So the typical player in equilibrium, their law is going to converge, their state process will converge in law to this normal distribution here. You can say more if you look at the empirical measure, so the random measure, the distribution of all of the players in equilibrium, then this too will converge to this non-random limit given by this Gaussian measure flow mu t. You can say even more. If you take any two arbitrary players, then if n is very large, these two players will be, their state processes will be approximately independent, each one given by, again, this Gaussian marginal law mu t that you compute from the mean field control policy. Okay, and so this gives you a pretty strong picture of how the convergence happens as n goes to infinity. But there's another direction you can go here, which is maybe a bit more common and easier to implement in models where you can't find things explicitly. This is this approximate equilibrium story that's become quite popular in the mean field game literature. If you don't need to be able to solve the n-player game, you can instead just directly solve this mean field game model to identify this say alpha MF control, as I called it. And then you tell each of your n players to ignore everybody else and just apply this control policy to their own state process xi. And if they do this, then what you get is not quite a Nash equilibrium. Each player might be able to improve their cost by a little bit, but not by more than epsilon. And epsilon goes to 0, like 1 over square root of n in this case. Okay, so this is kind of the usual mean field game picture here, how we would connect this n player game to its limit. And again, this is the complete graph case of these graph-based models that I'm talking about, where everybody's connected with everybody else. So again, the precise form of these laws and this control are not super important, but it's this picture here that we want to see if we can keep intact in some way as we generalize to different sorts of graph structures. So going back to now some arbitrary large graph. And well, what do I mean by large? In mathematics, large just means you have a sequence of growing things. So we have now a sequence of graphs, let's say with the size of the vertex set going to infinity. And the natural questions are, what of this previous story remains intact here? So a little more precisely, let's say we could identify the Nash equilibrium for the game posed on this graph Gn. Okay, then first of all, can we figure out what's happening to the distribution of a typical player's state process? Second, can we figure out what's happening with, how do we approximate this empirical measure? Is there some kind of asymptotic independence? And then in the kind of opposite direction here, if we, let's say, start from this mean field control, can we still get away with using that for each of our n players in this graph-based model? Will that still give us some epsilon Nash equilibrium for some epsilon which vanishes as n goes to infinity? And if this fails, then is there a different way we can construct a good, approximate equilibrium in some way? So these are the kind of main questions I want to think about here. And we're still not really at a well-formulated question yet, because this typical player idea kind of breaks down immediately when you move beyond this mean field case. So when you get out of this complete graph case, when players are not all interacting equally with each other, you immediately lose exchangeability. And this is a key issue in these graph-based models, is this loss of exchangeability, right? And the simplest way to think about that, if we have an extremely simple graph, let's say a 3-player game here, then basically, to these two guys at the end, their view of the network is pretty different. There's no reason they would behave in a similar way to the guy who's sitting in the middle here. Okay, so in general, players will behave differently in a graph-based model just because they're living in different parts of the graph. So we don't have exchangeability, so that even the meaning of this typical player is not so clear. Different choices of player will have different distributions. So this is sort of a first challenge that I'll return to a bit later, this lack of exchangeability. But otherwise, we have some reasonable set of questions to look into here on these graph-based models, and I'll give you an answer to the first 4 of them in this context, but not really 5 quite yet. Oh, and just as a side note, let me stress that here in this model setup, going back a couple slides here, we're interacting symmetrically with all of our agents. So with all of our neighbors. So we've moved past the mean field case by saying that we only interact directly with our nearest neighbors in the graph, but I'm still keeping the symmetry intact. You're still interacting equally with each of your neighbors. And for this reason, the graphon formalism, if you're curious, does not really make sense for us. This graphon framework is more suited to situations where you're not interacting symmetrically with your neighbors. So this is more of a side note where the graphon framework would fit in, if you're curious.
Daniel, there is a question from Harvey. Harvey, do you want to go ahead?
Yeah, I mean, just going back to that function that you're minimizing.
Mm-hmm.
I mean, intuitively, it would seem like if all the alphas go to 0, then of course everybody's going to be close to each other, as close as possible. So is that intuition really what's going on?
So I guess it's the noise that confounds that solution. If there were no noise here, then I think alpha equals 0 would be the solution here. But as soon as you see that one other player has been kicked away from 0, then you want to sort of move toward wherever the average is now. So the noise will keep you from really staying put.
Right, but then given the noise, then it would be some that are high, some that are low, and they're always moving around. So you'd still kind of, and since it's you're adding a DW there, that you would seem like you'd still have to converge to 0.
I guess it's the maybe the Markovian nature of the controls makes this a little more understandable. Why, if you see some deviations away from 0, then you can actually do a little better by chasing them rather than staying put at 0.
Right, in the short term, but you'd think in the longer term, everything is going to kind of quiet down and tends towards 0, right?
If we each behave in this way, though, of chasing the deviations, then there will be no kind of return to 0, in a sense. So
okay. Yeah, I can see what you're saying. Yeah. Okay,
yeah,
thanks.
this is the intuition I'd offer. When you work out the math, we will see that the solution is not just 0 controls for everyone.
Okay, thanks.
Sorry, it seems to scroll very slowly, so I got a little head start here.
Yeah, I wanted to mention that, make sure that you have about like maybe 15, 20 minutes max.
Okay, then let's get a move on it here. I'll skip this intuition here and jump straight into the first result, which is about these approximate equilibrium stories. So if we, the first result basically says that on dense enough graphs, we can get away with the usual mean field approximation. And what does that mean? Well, we take the same alpha MF, the same control that I told you was the solution for the mean field game. Take my word for it. Now, if we take any finite graph, this is really a non-asymptotic statement at first. If you take any graph, you play this game on the graph, but you tell every player to use this alpha MF control, then this will form an approximate equilibrium in a somewhat generalized sense, where each player gets their own little error term, epsilon v. And this epsilon v is a bound on how much player v can improve their cost by switching strategies, assuming that everyone else sticks with the same alpha MF strategy. So if I'm player v and I know everybody else is using alpha MF, then I'm free to do whatever I want, let's say, but alpha MF will be within epsilon v of optimality for me. And this epsilon v is just a constant divided by the square root of the number of neighbors I have. Okay, so this is a notion of approximate equilibrium. It's a little different from what you might have seen more often, which is to require a uniform bound on the epsilon, to say that there's a single epsilon and no player can improve by more than that epsilon via unilateral deviations. It makes sense here in this heterogeneous context to allow a different epsilon for each agent here, because the epsilon that you can get away with depends on your position in the graph, it turns out here. Okay, so this is the kind of cleanest, non-asymptotic version of the theorem. If you want to think asymptotically, then there are sort of two natural regimes to think about. The first is when the graph has you have a sequence of graphs with diverging minimum degree. Okay, then in this case, you can bound all of these degrees from below by this minimum, and then all of the epsilons are bounded from above by order 1 over square root of this minimum degree. Okay, so in the complete graph case, in the mean field case, this degree is n-1, so we recover this order 1 over root n that I mentioned before. But this gives you a pretty general criterion already for when you can get away with the usual mean field approximation. As long as the degree, the neighborhood size of each player is going to infinity, then somehow there's enough averaging. Everyone has enough neighbors that things sort of average out, and we get the usual sort of mean field approximation here. If you want to think in terms of the Erdos-Renyi graph, then as long as the expected neighborhood size is larger than log n, basically, this NP in an Erdos-Renyi graph, then this will give you this diverging minimum degree, but not if you have less than log n expected neighborhood size, because then this is the connectivity threshold. Then you'll have isolated vertices with high probability, and this minimum degree cannot diverge. So this is the Erdos-Renyi situation, but this really does cover quite a lot of cases. But if you're willing to allow the epsilon to depend on the name of the player, if you're willing to let some players have a higher epsilon than others, you can get to a sharper, let's say, denseness threshold. So what do I mean by this? Well, let's say we have a sequence of graphs, and instead of requiring the minimum degree to diverge, which is kind of an L infinity requirement, we instead just relax this to like an L1, somehow the average degrees diverge in a certain sense, really 1 over the square root of the degrees on average should go to 0. Then in this case, the average of the epsilons goes to 0, which this is a reasonable notion of approximate Nash equilibrium. Basically, certain players might be able to achieve some non-trivial gain in reward by switching strategies, but a vanishing fraction of them will be able to do so. Okay, so certain players might have epsilons which do not go to 0, but very few of the players will be like this. So somehow on average, the epsilons going to 0 is still a very meaningful notion, weaker one, but a meaningful notion of approximate Nash equilibrium. And this is achieved at a much weaker denseness threshold. So in this Erdos-Renyi case, you don't need the expected neighborhood size to be bigger than log n anymore. All you need is that it goes to infinity at any rate at all. And this will be enough to be sure that this mean field policy gives you an approximate equilibrium in this generalized sense here. Okay, so the short message of this first result is that, yes, on dense graphs, you can get away with the usual mean field approximation to construct an epsilon equilibrium. But if you zoom in and really define what do I mean by dense and what do I mean by approximate equilibrium, depending on what kind of notion you want to work with, you have different different versions of this result, basically. The weaker the notion of epsilon equilibrium, the sparser the graph can be to still achieve this. Okay, so this is kind of this is the first main result, the sort of easier one. In the rest of the talk, I want to discuss a bit of what happens in the setting of really trying to exactly identify what are the equilibria in the n-player game and what are they converging to. Okay, and this is a more difficult problem, but for certain nice enough kinds of graphs, we were able to really explicitly compute the equilibrium for these n-player games. And these nice enough graphs need to be symmetric enough. And this goes back to this issue of the loss of exchangeability that I mentioned earlier. Basically, the problem is that, on the complete graph, in the mean field case, everyone interacts equally with everyone else. So if you permute, if you rename all of the agents arbitrarily, everything looks pretty much the same. In these graph-based models, you don't get exchangeability, but you kind of inherit any symmetries of the graph itself. Okay, and the way to formalize that is through the notion of an automorphism of a graph. So this is just a little bit of algebraic language that clarifies the whole picture, I think. An automorphism of a graph is just a bijection on the vertex set that preserves the edge structure. And the basic idea is that if you have an automorphism, this is like a relabeling that respects the graph structure. Then if we relabel all the players in a way that respects the graph structure, then in equilibrium, we should get exactly the same joint distribution of all of the players here. Now, in the complete graph case, any permutation at all works as an automorphism. So we get any permutation here, and this is the notion of exchangeability. But on a general graph, this is only some kind of partial exchangeability. You have a smaller group of automorphisms that's respected by that you have invariance with respect to here. Okay, so there's this very useful notion that we ended up finding that works very well for us, which is this notion of transitivity, which basically says that any pair of vertices can be mapped to each other by some automorphism. And heuristically just means that the graph looks the same from any vertex's point of view. I'm low on time, so I'm going to be a little brief here and skip some formalities. The good examples to keep in mind are, again, this complete graph case where all of the permutations work as automorphisms, and this invariance property is known as exchangeability. Another good example is this cycle graph, where again, we're all sitting around some round table. This is a nice graph. This is a transitive graph. It looks the same no matter where you're sitting. You're still sitting around the same kind of table structure, whatever seat you're in. The automorphism group is known as the dihedral group in this case. So the cycle graph will work for us. There are many other transitive graphs out there. Basically, this transitivity gives you this property that everybody's marginal distribution will be the same, because there's some relabeling of the graph that takes me from my position to your position around the table. So it's not true that the whole joint distribution is invariant under permutations. It's just true that everyone's individual marginal will be the same if we have this transitivity. So this is much weaker than exchangeability, but it's still like enough symmetry to really do something nice and tractable, it turns out, for our purposes. Okay, so there's I want to state then the kind of main theorem in this direction, which requires a little bit of notation, mainly this notion of the Laplacian matrix of the graph, or the so-called random walk Laplacian matrix of the graph, which is, if you look back at this cost structure, where you had your own position minus the average position of your neighbors, this is exactly minus the Laplacian multiplied by the vector of positions in component V. So this Laplacian matrix shows up really in our cost structure here. This is like the rate matrix of the continuous time random walk on this graph. Okay, so this is related to the adjacency matrix. Let me not dwell on this too much. In terms of this Laplacian matrix, we can state really, we can identify the Nash equilibrium for our model. So this is the kind of harder theorem in our paper here. If we take any finite transitive graph, so again, transitive is this nice symmetry assumption, then we have a semi-explicit solution for our model up to a solution of an ordinary differential equation. So this Laplacian matrix shows up here in the definition of this function Q, which is like a normalized characteristic polynomial of this matrix. And then we use this function Q, or really its derivative, to solve this ordinary differential equation for F. And then once we do, we define a certain matrix function. The precise form is not super important, but just depends on F and this Laplacian matrix L once again. And then this matrix basically determines the Markovian control. You multiply this matrix by the vector of state processes, and in the V component, that's what your control should be if you are player V. So this is a Nash equilibrium. I don't know if it's the only one. It probably is, but we don't have a proof. And this is really a very explicit Nash equilibrium where the state process has this multivariate Ornstein-Uhlenbeck form. Okay, so this is semi-explicit, and this is nice on the one hand because it's pretty explicit. On the other hand, it's not obvious at first how you would do some sort of large-scale limit based on this solution. So the last thing I want to convey is sort of how you would actually be able to do this. This does actually lend itself fairly well to a large-scale analysis. And this comes from one key observation or two here, which is that pretty much everything I wrote on the previous slide can be expressed in terms of the empirical measure of the eigenvalues of the Laplacian matrix. So this perspective turns out to be very useful. So this Laplacian matrix, you can show without too much trouble, has real eigenvalues between -2 and 0. You repeat them by multiplicity, so you have n of them, and you form the empirical measure. Okay, now, first of all, first key point is that you can write everything in terms of this measure. Well, what do I mean? Well, first, you can take this function Q that I mentioned that governs this F function. And this Q is a determinant, which you can write, or a normalized determinant, which you can write as a geometric mean in terms of these eigenvalues. And then if you take the exponential and log to turn this geometric mean into an arithmetic mean, then you can write this in terms of an integral with respect to this eigenvalue measure here. Okay, so this we've rewritten then in terms of this eigenvalue distribution. I guess I'm running low on time, so I'll just mention you can do the same thing for the distribution of a single player state process, and this uses also the transitivity. So each player will have the same marginal law, and you can identify it as a centered Gaussian with mean 0 and a certain variance, which comes from like the normalized trace of this covariance matrix, which can be again written in terms of an integral over this eigenvalue measure. Okay, so that's observation number 1, that everything can be written in terms of this empirical eigenvalue distribution. Observation number 2 is that these things are actually converging to something in the large scale limit in many reasonable cases. So basically the next main theorem will say that if you have some sequence of graphs for which the eigenvalue distribution converges weakly to some limit, to some limiting probability measure, then all of the quantities in our Nash equilibrium will also converge to some equilibrium, to some limit, which can be identified in terms of the limit of this eigenvalue measure. Now, this is useful because, again, many natural graph sequences have, tractable spectral measures and limits thereof. So a first simple example would be the complete graph, where you have just, 2 delta measures which converge to a delta at -1 for the spectral measure. More generally, you can show for transitive graphs that the eigenvalue distribution converges to a delta if and only if the degree is divergent. Okay, so dense graphs basically in this transitive context are those whose spectral measure converges to a delta. And the mean is always -1, so the delta has to be at -1. So this dense graph case is identified by this 0 variance limit for the eigenvalues. A more interesting example then is the cycle graph case, where you can compute the eigenvalues exactly for this Laplacian matrix and identify the limit as some sort of arcsine law. So this is another good tractable example. And there's a related computation for, let's say, the d-dimensional torus, where d equals 2 gives you back the cycle case. Okay, so this is sort of to convince you that this next main theorem, which I guess I'll just sort of put it up and end here. This is sort of then a reasonable limiting analysis, because in many of these graph sequences we're thinking about, this eigenvalue distribution does converge to a tractable limit. And then in terms of that limit, we can identify kind of what we would want to in equilibrium, the distribution of a typical player, as well as the empirical measures limit, which is again this non-random Gaussian measure. So there's again this there's a sort of propagation of chaos here, where the empirical measure converges to a non-random limit. There are some interesting subtleties behind that I don't think I have time to discuss, involving the fact that the correlations between players decay as a function of their distance in the graph, which is a key point behind the scenes here. But in any case, there I think here is some interesting first steps towards understanding these large scale graph-based models. With this, I'll try to gracefully jump to the last concluding slide here, which is just to summarize that, again, it seems this mean field gain policy will work pretty well on dense graphs. True equilibria we can analyze for dense or sparse graphs using this spectral approach, which seems to be very, very convenient, although maybe limited to linear quadratic models. This is not quite clear yet. But there are many questions remaining. There's a big challenge here, which is that the controls generally don't just depend on your neighbors, they depend on everybody in the whole graph. And there's kind of no way around that, it seems. And what I have not found yet here, given you any hint of, is what would be really a self-contained like limiting model in the sparse regime, like some sort of analog of the mean field game model that you can analyze on its own without first studying the n player game and passing to the limit. But nonetheless, I think there are some interesting first steps in the case study here. So if you're curious, I'll refer you to the paper. I'm happy to answer any questions you might have. Thank you for your time and attention. I'll end here.
Thank you very much, Dan, for very nice talk and very nice results. I must say too. So
thank you.
We'll have, as usual, several minutes to the hour for open questions to the entire public. You can ask them directly or type them in the chat. I see Andrew wrote a question, and we'll give him in a minute. And after that, we'll stop the official recording part, and off record, we can ask further questions or criticize the talk or not criticize after like 5-6 minutes. Andrew, why don't you ask your question, please? You have to unmute yourself, probably. We don't hear you. But Daniel, the question is also in chat. Maybe you could.
Yes.
You
So
could
I guess
it.
right. So since exchangeability is lost, then the joint distribution does need to be defined. If you have n players, then their joint distribution will be on Rn. Now I guess when you have exchangeability, you can somehow, by looking at the empirical measure, you can embed everything into the space of probability measures on probability measures on R. And this is maybe what Andrew's hinting out here, which is not possible in this setting when you lose exchangeability. But the perspective I've taken here sort of avoids the issue of this very large space of non-exchangeable distributions.
Well, I think my sound should be fixed now. Is it? Can you
Yeah,
hear
yes,
me?
I can hear you.
Well, I apologize for that. So I just wanted to get some intuition behind this. So so you still have to have some reduction, right? So you cannot deal with the names of all players, and if those are the nodes on the tree, so is it that the automorphisms, they reduce the tree to a group? Is this what is happening?
I would give you two answers. There are two ways we're sort of reducing the complexity or dimension. The first way is with this transitivity assumption, which ensures that every player has the same individual marginal distribution. So you can really then talk about a typical player without any ambiguity, because the choice of player will not affect the one-dimensional distribution. So that's resolution number one.
Okay, just to clarify, so this removes the graph structure from the picture.
Well, it doesn't remove it so much as ignores it. When you just talk about the law of one player.
That's what I meant. So in the end, in the limit, there's no graph structure. Yeah. Okay, sorry. Yeah. So what was your next other?
The other way we're getting around this is just with this usual trick of symmetrization. When you study the empirical measure, right? You can, if you take a vector of n components and apply a random permutation to them, then you recover exchangeability, but the empirical measure does not change. So in this way, you can sort of pretend things are exchangeable for certain computations, like when you're studying the empirical measure. And
so ultimately your empirical measure is still on what, R1 or R?
Exactly, yeah. R1.
Okay. All right. So thank you very much. Thank you.
Thank you. Thank you. And we have, let's take one more question, Ryan.
Yeah, so to start off, you have a graph and you have this game on, each vertex of the graph is an individual agent. If you instead think of each vertex as itself being a continuum of agents of that type, is that equivalent to what you're doing, or is something different going to happen? And is there maybe like a limit of your games that converges to that sort of game of different types?
Yeah, this is a good question. I suspect the latter would be true, that somehow if you take a large enough graphs where you have a bunch of different very dense subgraphs somehow involved in it, then this could converge to the model like what you described. Let me mention though that the model like what you described is the one studied in a lot of the work, the papers so far of Keynes, Gao, Huang, and a few other authors that they've called graph on games. There's sort of two different types of graph-on games in the literature, and the ones that they've studied the most are indeed like you've described, where each vertex or each player is really now a continuum of players in some sense. So I think there's a connection here, but I guess these prior papers really start somehow from the continuum model and then work back to the n player game that would converge to it. And I'm trying to just start from some generic n player game on a graph and understand, what's going on there, heading to the large scale limit. So in that sense, I didn't find it that natural to blow up each vertex into a continuum.
So theirs is almost more of like a direct, consideration of an infinite player, like mean field thing, and so it's less maybe less natural or less real. Is that kind of the?
Yeah, I guess in my context, I would say it was less natural to think in those terms, since I was starting from the finite population, whereas indeed they were starting from the continuum. That's how I'd answer.
Okay, so all right, let's take one more question, Tanya, and then we'll stop the formal part. So
yeah, thank you very much, Daniel, for the very nice talk. I have a quick question. Is there a hope one could put these games, whether they are the approximate games or hopefully the games in the limit, in the realm of equations?
Right. So, an HJB equation or FBSD or something of this sort.
That's right.
Right. This is a good question. So so I guess for each finite graph, you could in principle write, if you have a graph on n vertices, then the value functions of your n players could be described in terms of a system of n coupled HJB equations. This is, I guess, there's a now sort of usual way in a finite population stochastic differential game. You could write down an n-dimensional HJB system.
But would you need to to consider equations on graphs?
Right. So in the limit, this is not so clear yet. So what some of these guys have done in the graph-on mean field game literature, Keynes and Huang and some of them, is to consider now your limit model as a graph-on, which is really a graph with a continuum of vertices in some sense, and a function representing edge density. And what you then have is, a continuum of players indexed by the unit interval. And for each one, you have a value function that solves some HJB equation. And so now you have a continuum of HJB equations that are coupled with each other. So this is the closest thing, I guess, to an equation for the limiting model yet. And to me, it doesn't represent a huge simplification, because you've passed from a large finite population now to a continuum of PDEs, rather than like a single representative player like we have in mean field games.
Yeah.
So this I would lump in with this last bullet point on my slides here, which is that there's not yet really a proper limit model for sparse regimes, but maybe also in the dense case, there's still things to be understood in terms of how to really write like a concise equation, PDE or otherwise, to encapsulate the model. This is not really understood yet.